Hi, Leonardo. Welcome. All right, welcome. Good morning. Welcome back. Joseph, if you're here, please let me know so I don't mark you inaccurately. I'll be as accurate and precise as possible in everything I do, not just in chemistry measurements, but my attendance over here too. So just want to make sure it's accurate. Joseph, if you're here, you could unmute yourself. Make sure to make a mistake. All right, so welcome back. Hopefully you had a great weekend. Hopefully you took advantage of that nice weather that we had. It's hate to say it, but this weather is not going to last for too much longer. It's going to turn real cold real quick. Hopefully you put an extra blanket on your bed. Hopefully you're all ready to roll for the turning of the seasons and that colder weather, which is going to happen. All right, so welcome back to the best class today. Here we are ready to roll. And today's agenda, before I get there, there's the open house video. If mom, dad, or grandma want to check that out, know more about Mr. Brown or teen chemistry, or because he's just a really cool teacher, you want to show, hey, this is my teacher, he's cool. You can do that if you want to. If you don't want to, it's totally fine. I'll leave this up there for another week. It's there. All right, today's agenda. We're back. The quote of the week comes from Marie Curie. She actually has ties to this area, so she's a pretty, not just pretty, but I don't know if she's pretty or not, but she's a pretty famous female scientist, and she has roots in this area as well. So when she was doing her studying, she actually came, she's not from America, but she came over from Europe over to O&D Young. It's a small school, a little south from here. It's in between Richfield Springs and Ilion. So O&D Young, she actually went there. She actually did some studying there as well. So she does have some ties to the area. So I think that's pretty cool. This area is very rich in history. Just got to dig a little bit to get into it. All right, her quote was, "Nothing in life is to be feared, it is only to be understood." So you're going to encounter things in life that you just don't know, or things that look really scary. But if you start to dissect it little by little, break it up little by little, or get informed with it little by little, then it won't be that bad. So when you have challenges in life, start opening things up little by little, ask yourself questions, why, how, and then you'll be more comfortable with it and it won't seem so scary anymore. All right, the daily agenda for Monday, October 19th, 2020, day one. We are going to continue on with matter and energy. We will finish this unit this week. We are continuing on with topic number 6. We have a couple YouTube videos we will play. We need our guided notes, and there's going to be examples we'll analyze as well. Hopefully by the end of today's class, you will have an exit pass that you should be able to complete for class today. The attachments are below. I will play at least 2 videos. And I'll play a third one as well. The examples are below as well for today's class. And I didn't put the exit pass up there. I'll do that at the end of the day today. So the exit pass will be assigned up there too. Please get the Google Doc page, the Unit 2 Matter and Energy Guide notes. Get that out, get that ready to roll. You can find that in a couple spots. You can find it on your drive, or you can find it under classwork. So your drive will have that document up there. Or you can go under your classwork and you can find this document too. All right, so this is my notes, our guided notes for this group. We went through matter, topic 1, done, check mark that one off. We did topic 2, mixtures, check mark that one off. We spent some time going through percent air and temperature conversions, done. We talked about heat, which was Q, and energy. We analyzed some formulas for that. We went through topic 5, heating curves and cooling curves. And today, we'll definitely focus on ideal gases. What's left ahead of us is vapor pressure, and the last one is density. I'm going to throw in there too, which is a really easy formula. So next class, we'll go through vapor pressure and density. After that, so that's going to be Tuesday. The next class is going to be a lab, and the next class is going to be, so lab and review will be one day. The class after, the third class this week, will be devoted to a test. So you'll have a test in this unit, a lot of material here. So all these exit passes that you completed, those will be on the test. So maybe like 3 or 4 questions from each topic, maybe 5 if it's a popular topic, and they'll be make up your test. All right, topic 1, we went through the measurements. We talked about mass, we talked about extensive properties, intensive properties, physical properties or something you see, chemical properties or something that change. We talked about the phases of solid, liquid, and gases. Solid particles are tightly packed together. Liquids are free flowing, there's no space. They have a measurable volume, obviously. And gases, they take the shape of the container. And they're always moving. The topic for today, we're really going to focus in on gases. So that diagram we're actually going to recreate, and we're going to explore ideal gases, so kinetic molecular theory. So we'll actually use that later today. We talked about physical and chemical properties. We talked about homogeneous and heterogeneous mixture. We talked about ways to separate mixtures by filtration, distillation, and chromatography. We talked about an element and compound. Next element, we're going to talk about the atom, which is going to be a lot more about the elements. So that's the next unit we'll talk about next week. We talk about breaking down compounds into 4 different types of formulas. We talked about substance versus mixture. We talked about law of conservation of masses. We highlighted the reactant to a product. The mass on the reactant side equals the mass on the product side. And in every chemical reaction, mass, energy, and charge is neither created nor destroyed. We did some percent air, some fall colors. We did some temperature conversions. The middle one's the one you should know. We talked about heat of fusion, vaporization, and specific heat capacity in terms of formula. We analyzed several examples. We took a look at a heating curve. You labeled the phases of the heating curve. We took a look at a heating curve in terms of energies, kinetic energies, energy, and motion. So hopefully you analyze that. And we analyzed a cooling curve with phase transitions and a cooling curve with energy associated with it as well, kinetic and potential energy. We left off on topic number 6, which is ideal gas laws. My goal for today is to definitely get through this page, and we'll probably get through this page as well. Hopefully I have more time to analyze more examples on this too. All right, so ideal gas laws. Before I even start today's class, I'm going to jump start with a video, a flick to get those molecules rolling, those particles rolling for today.
In this video, we're going to look at the 3 states of matter: solid, liquid, and gas, and see how substances can change from one state to another. To do this, we're going to use a model called particle theory, or sometimes kinetic theory, which helps us explain how the particles in each state behave, by considering each of the particles as a small, solid, inelastic sphere. In solids, there are strong forces of attraction between the particles, which holds them all close together in a fixed position to form a regular lattice structure. And because the particles are fixed, the overall substance keeps a definite shape and volume, so can't flow like a liquid. The particles can vibrate around though, so you can imagine them constantly jostling against one another. Now, if we heat up a solid, its particles gain more energy and start to vibrate even more, which weakens the forces between them. And at a certain temperature, which we call the melting point, the particles will have enough energy to break free of their bonds, and so the solid melts into a liquid. In liquids, there are only weak forces of attraction between the particles, so they're free to move around and are arranged pretty randomly. However, the weak forces of attraction do mean that the particles tend to stick together and are fairly compact. This means that they have a definite volume, even though their overall shape can change, allowing them to flow to fit a particular container. If we then heat up our liquid, the particles will again gain more energy, and this will make the particles move around faster. which weakens the forces holding the particles together. Then, once we reach the boiling point, the particles will have enough energy to break the bonds altogether, and so the liquid boils or evaporates into a gas. In gases, the force of attraction between the different particles is very weak, so they're basically free to move around by themselves. This means that gases don't keep a definite shape or volume, and instead will always fill a container, as they spread out as much as possible. Now, we normally say that gases are constantly moving with random motion, which is a bit confusing because gas particles actually move in straight lines. They don't randomly swerve. What we really mean by random motion is that the particles can travel in any direction, and they'll end up being deflected by solid walls and other gas particles randomly. When we heat up a gas and the particles get more energy, and so travel faster, the gas will either expand if the container it's in is expandable, like a balloon, or if the container is fixed, then the pressure will just increase. On the other hand, if we cool the gas down enough, then the particles won't have enough energy to overcome those forces of attraction between them. And so bonds will start to form between the particles, condensing the gas into a liquid. As we cool down the liquid even further, the same thing happens. The particles won't have enough energy to overcome the attraction between the molecules. And this time, even more bonds form, fixing the particles in place and freezing the liquid into a solid. Now, the last thing we need to mention is that if we're working within a closed system, changes in state won't change the mass at all.
I'm sorry I'm late.
The same number of particles. However, the density of the substance will change, with solids having the highest density, liquids having a slightly lower density, and gases having the lowest density of all three. That's everything for today's video. So if you enjoyed it, then do give us a like, and hopefully we'll see you soon.
Okay, so there's solids, liquid, gases. Talked a little bit about energies, obviously there, and some density, which we'll get into next time or time after for class. All right, so moving on forward. Hopefully you have that page all set for your Google Docs, ready to roll. I'm also going to open up my Unit 2 Matter and Energy slides. So hopefully by now you have a good setup for your class. You're feeling confident about this class. Hopefully you feel it's organized. I honestly am loving this setup, but I just miss the little interaction with you guys, seeing you face to face, and probably would have some more corny jokes if you guys are live in class face to face like that, but it's okay. But anyways, I'm enjoying it. Hopefully you're picking up a skill here and there. We're definitely doing a lot of cool stuff here, I think. All right, so find out where we left off. Topic number 6. I'm scrolling there. We're almost done. We're almost at the end of the unit, so ways to go. All right, there's my guided notes, and we'll pick up where we left off last week. Topic 6, ideal gas laws. All right, ideal gas laws. Kinetic molecular theory is going to be observed by the behaviors of gases. So how gases behave, the way gases behave is described by this theory, which is, what doesn't show up, John? Your Google Docs? Is anybody else experiencing, I'm sorry, someone's privately messaging me, so I just, is anybody else experiencing their Google Doc not uploading or not showing up? pardon me, I'm just gonna look at somebody's work really quick. Take a minute break. I'm just gonna look at someone's work really quick. I don't want to pull all the grades up there, so I'm splitting just the screen for the Google Slides. John, I'm seeing your document. It has your stuff in here. Sorry about the side conversation, everybody else. It looks like it's complete. I don't know why you can't find it. Let's see, did you go to your Google Drive? I guess I could try to send it back to you.
This is in our notes.
This is going to go in our guided notes, but I'm trying to help somebody out. Well, one student right now, that's why I'm a little off right now. So guided notes, yeah. John, try to refresh your screen up on top, your toolbar and stuff on top. I'm really not sure why, but yours has the same setting as everybody else in your class. It says assigned. I can't return it to you for some reason, but you're all up to date. Maybe try restarting your computer. Try getting starting to refresh. Not sure on that one. But all your stuff I could see, John. I can see all your edits there. And I don't know what the, I'm not sure. Maybe bad connection, I'm not sure. But just so you know, I could see everything where we left off, and I don't know what else I can do right now at this time. But I'm gonna continue on. So moving on forward, sorry about that, John. Hopefully, maybe at the end of class I can help you through something. If you can't get anything up there right now, maybe you just wanna watch a video and we'll talk about it later. It's up to you. All right, so I think you guys had enough time to get that in there. But anyways, kinetic molecular theory is a theory used to explain the behavior of gases. So again, please highlight your information as you put it into the text. The behavior of gases. So it works. John wanted to stall me for a few minutes just to say hi. Just kidding, John. That's fine. I'm glad it works. Behavior of gases. So how gases behave is kinetic molecular theory. So kinetics means energy and motion. So kinetic energy is energy and motion. Kinetics, I think of something moving. Molecular is something really small. And then the theory is an idea proposed. So things that move at a small level. Specifically gases. So gas particles. So gases contain particles that are in constant random straight line motion. So please fill that in there. I know you guys already have it. Constant random, and they're in straight line motion. So they don't move in circles. They just go straight back and forth. That's why I put those little arrows on top of the gases when we did them. So a lot of times when I did like solid, liquid, gases, I did them like all over the place. They should have been more like a side to side. When it hits a barrier, then it veer off. So once it hits something else, it goes in a straight line motion. It's not like circular motions, not like that. It's got to go straight line until it hits a barrier type of thing. All right, once you know that, we're going to double click on that text box to the left. So that text box to the left, click it twice, left click it twice, double click on it. And again, we're going to represent the gases. So now we're just focusing on the gases in the cooling curve or heating curve. Once you click on that, click on it again to get the blue box around it. And now we're going to add a circle for a particle. So again, I went to insert, went to shape, shapes, and I did an oval. I am going to recreate a circle. Guess I'll be a smiley face instead. Switch it up. Fill it with yellow. There's my emojis for today. So there's one gas particle happy. One happy gas particle. All right, what I'm going to do now, I'm going to highlight that. You don't have to do the smiley face. I don't care. Maybe you're not happy today. So be it. All right, so I'm going to click on that. I'm going to hit Control C. I'm going to hit Control V. Let's do it 6 times. So a lot of times in the regions, they'll ask for, in a box like this, they'll ask for a particle diagram for a solid, liquid, or gas. And they'll say, draw at least 6 particles. So when I represent the gases, I told you think of the like number 5 dice. But if you only put 5 particles, that's not going to really be enough. It's not going to give you credit. Even though if it looks like this, that's a number 5 dice. You still need more particles in there. So this time I'm adding a couple more. I don't care how you represent it. When they're spreading out, something like that, that would give you full credit for the regions. So that would be like a gas particle.
So we can just spread them like anywhere as long as they're far apart.
Yeah, they're not going to all be like at the top though. They're going to be like spread throughout the entire chamber. So yeah, spread them anywhere you want. This doesn't have to look like number 5, but the 5 dice. I just say that just to get you guys thinking, spread them on out, because number 5 dice, you really have them spread out pretty good. I don't know where I want these now. It's bothering me. Spread them out. It's fine anyway. Just like this is totally fine. I'm gonna leave it like that. All right, the next thing I'm gonna do is add some arrows here. So if I go to the segment, select line, and then arrow, I'm just gonna draw some arrows in here. If they ask for a gas, you can represent it just like this. I put the arrows in to represent these things are really moving pretty quick, or they're constantly moving. So I don't care the direction of these arrows. I don't know if they go anywhere they want, but they are moving in a straight line. Maybe this guy's gonna bounce off this wall and then switch angles, and it's gonna go maybe this way. I don't care. So these are just representing these guys are constantly moving in this chamber. And this one bounced off the top wall and ricochets back on down. I don't even care if you guys put the arrows in, but I just like to do it just to show that they're moving. These little happy gases, kind of like yesterday over in West Winfield, there's some gas that was dissipated. There's a leak in the gas valve for a company that's in Tennessee. So they get the natural gas from, I don't even know where, but there is a line in West Winfield, which is south of here as well, about maybe 20 minutes past Sequoia, that had a leak, and maybe you smelled at your house. It was a gas smell, natural gas that was leaking from the pipe. But anyways, these gases, you smell them, and I think it was a cloudier day. That's probably why it helped stay down in the atmosphere. If the clouds weren't there, it would have dissipated a little easier. But back to this, these gas particles, you can see the motion of them. Once you're done with that, please save it and close it. If anybody wants anything repeated here, I'd be happy to do that for you too. You just chat it to me, you can chat privately or whatever you want to do. Oh, that's cute. All right, so those are gas particles and how they typically move. When I think of kinetic molecular theory, I always think of these gases because it's going to help you out in the theory as well. Kinetic molecular theory. I don't need this last one here, so I'm going to delete that one. That was part of the last bullet. Gas particles. Gas particles collide with each other and with the walls of their container. So gas particles collide with each other and within the walls of their container. So there's a lot of collisions there. These guys, they hit each other a lot. Gas particles collide with each other and the walls of the container. There's a lot of collisions between these particles. Why? Because they're moving. Like solid particles, they're not going to collide as often because they're more at rest. Solid particles, they're there. They're not going to find other people to collide with because they're stuck together. Liquids, you'll have a little bit more collisions there. There's going to be more frequent hits because they're just hanging out on the bottom of that box. But gases, since these guys are ripping all over the place and going and moving quickly, there's more collisions. The collisions may result in a transfer of energy. So when these things collide, they don't just collide and not disperse the energy. It transfers, it gives off the energy when they collide. Transfer of energy. They typically transfer all the elastic potential kinetic energy. That means it transfers all the energy when they collide. So what the heck does that mean? So if I have a particle, for instance, just hanging out and not moving at all, so that velocity equals 0, and then another particle comes on in, traveling at like 10 meters per second. Let's try that again. 10 meters per second coming on in. It's going to hit and transfer all that velocity in the other one. So this one will now be moving at 10 meters per second. This one's now at rest. So again, Newton's laws of motion. This comes in at 10, hits it. This one's at rest. This one moves at 10 meters per second in the other direction. It transfers the energy. Next one up, the gas particles are separated by a relatively large distance. They're not all hanging out in the same spot. They're separated by a large distance. You could see that from this diagram right here for gases. They're separated at a relatively large distance. Separated by that relatively large distance. And next, gas particles do not or are not attracted to each other. Do not attract each other. So these guys, there's a lot of fighting in here in this little container. They should probably be sad unless they guys like to fight. Kind of like, that's why people were late for class today. There's a fight in the hallway at Proctor, so it was a little chaotic. This is chaotic up here. So if there's a fight at Proctor in the hall, sometimes it gets a little chaotic in the hallways, and you guys get a little excited, get a little tension, but hopefully not. There's no reason to fight. But anyways, kind of like these gas particles, they're always colliding and running into each other and bouncing off. So a lot of times you're walking through a high populated area, you might be rubbing into someone's shoulders when you walk on by. You're not gonna, you might say sorry. You should say sorry if you run into someone, but you say sorry, you keep walking. There's probably not gonna be much of a connection there as you walk on by. You hit someone, you walk on by with your shoulder rub. Sorry, excuse me, whatever. So they're not attracted to each other in this situation. All right, next up is relationships between gas particles. Relationships, we'll analyze 3 different relationships. I'm gonna throw some bullets here. You don't have to as well. So the first relationship is for pressure. As the pressure of a gas increases, and we'll give you an example about this as well, because a lot of times students can't visualize pressure very easily. As the pressure of a gas increases, the number of effective collisions increases too as well. As the pressure of a gas increases, the number of effective collisions increases as well. So I added a new term here. It's effective collisions, a new word. The number of collisions is going to increase. So as pressure increases, there's going to be more collisions or effective collisions. What's an effective collision is if like 2 particles hit, like radon. If they both were a direct hit, that's an effective collision. So you and your friend walked right into each other, face to face. that's an effective collision. If you and your friend just brush shoulders with each other, that's not effective. You and your friend walk face to face in each other in an accident, effective. You brush shoulders, it's not effective. Just like these atoms or particles. In order to be effective, it's got to be direct hit. We'll talk about that a little bit later too. In terms of pressure, let's talk about this one. We'll actually draw something about this too. So I'm not going to give you time to copy all these other ones down. I'll give you time a little bit later. So first bullet says, as pressure of the gas increases, the number of effective collisions increases. Below that, I'm going to go just hit enter a couple times. And I'm going to put a little drawing here. We're going to draw something right now. I'm going to insert drawing new. Insert drawing new. This is my like blank piece of paper. You can tell I'm a little artistic here, I guess. I make these diagrams or whatever. Hopefully you're picking up on these little things too. All right, the first thing I'm gonna do for my drawing is gonna take a text box.
Wait, hold on.
What's up?
Wait, where are we inserting drawing on?
All right, so right below this relationship one, we went through the first bullet. So what we're gonna do now, so right below that first bullet as pressure, I'm gonna press enter a couple times. Anywhere in this relationship section here, so insert drawing new. Now you know where I'm at, right? I'm gonna add a text box. I'm not sure who's talking right now, but you could type it in the chat. You're breaking up a little bit on me if you have questions. All right, so next I'm gonna go to text box. I'm gonna add a rectangular vertical text box. Kind of like that. I'm gonna lower it down a little bit, but start off with that one. So take a text box. We'll make a rectangular vertical text box. I'm gonna leave it, if it's not highlighted, just make sure it's highlighted on the blue, a blue box around it. I'm going to change the color to black border, and I'm gonna change the weight of that box to something a little bit thicker, so it pops out a little bit more to 3. So again, there's my text box. Made a text box by just like that, T, and make a vertical text box. And
We're
then
making two.
What's that?
Are we making 2?
No, I'm just replicating what I just did.
Okay.
And then I'm gonna change the color and change the width of it. Okay, that's the first one done. So I only need one, good question. Now I'm gonna add another text box with a T. And this text box is gonna go from side to side inside.
Where are we putting this?
The second text box or the whole diagram? All right, so where am I putting it? This is going to eventually go at this point right here. So in relationships, I did insert, drawing, new, and then I have this so far. All right, so anyways, you have that first rectangle. The second text box again, I'm going to put from side to side inside my other one. So I'm going to take that text box, put side to side. I'm going to change the color to black. And additionally, I'm going to fill it with black paint. So you have that so far. Questions? If anybody wants to see anything again, please let me know. Okay, next up to represent this is going to be a chamber like a piston or maybe like a bike pump or something. I'm adding another text box and I'm making a really narrow rectangle on top. Try to put it in the center if you can. Center of that little. So let's try to replicate something like that. I'm gonna paint this one with black as well. So this would be like an engine. This chamber here is like an engine. It's like a piston in the engine, or it's like a bike pump or some sort of pump. They could pump up some tires, make balls. When you have that driver on top, which you can press down and up. Down, go tss, you release it up. You take more air in. Press it down, tss, gas comes out to fill up your bike tire. You release it, you get more particles. Before I pull this on down, we'll do a second diagram in a second. I'm going to add some particles to this. So I'm going to shapes. I'm going to add some ovals here. I'm not going to do the smiley face to be as cute this time. Make some gas particles. Make a nice circle. I'm going to fill it in with a color. Make one that you like, and then we'll copy it and paste it maybe 7 times. There's the first one. Click it. So again, just make one. Click it. Hit Control C. That copies. Then hit Control V 7 times. 1, 2, 3, 4, 5, 6, 7. So this is a spot where the gases are going to hang out. Take those 7 particles and just place them within that chamber. Spread them on out. You know they're going to take the shape of the container. They're not going to hang out at one spot. This is a closed container. So it's similar to the concept of like a bike pump, but a bike pump has a valve where you could release some of the gas. This one we're pretending it's closed. What if my gas particles in that chamber? As you're writing this, I'm going to go back to this in 1 second, but I want to give some other people like a chance to really think about what this process is going on here or what this should look like. Don't save and close yours. I'm going to save and close mine for a second. I want to show you what a bike pump, how it works, just in case you have never used a bike pump before or something like that, a little pump. This is what it's going to be like. So I'm going to save and close it. Please don't save and close it. Or if you do, we'll go right back to it. So I'm going to pop up on YouTube. YouTube. I'm going to go to bike pump. Bike pump. Let's see what pops up there. Place appropriate here. There's some nice pumps there. How to pump.
Take 126. Should I use my hands more with?
Oh, that's nice right there. That's all I need right there. So she's fooling around a little bit. It's fine. But anyways, this bike pump right here, you have that little lever that goes up and down. Let's see here. So up and down. So once it was all the way up, you had a lot of space in there for those particles to hang out. So once that, rewind it for 1 second.
Would that help?
Darn, it's too late.
Would that help?
All right, right at that position. Maybe that top of the, or the bottom of the lever is there. Inside that, you have some particles, just like we just drew there. So maybe that's the rod. Here, it goes up and down. These particles are taking the shape inside that container. As she presses it down, let me erase some of these now. So I don't know how many particles I have in there. Great, got rid of it all. Time is off a little bit. I thought she could all the way down there. Whatever, let's pretend she pressed it further down. You hear that? That's air coming out. Maybe she pressed it all the way down to here. Where's my cricket? So there's the rod, but those particles, however many you had before, there's just less space in there. And we're just going to represent this in the diagram. So that's what goes on with a bike pump. This is a great example of pressure and analyzing pressure with it too. So that's why I played 3 seconds of that video. All right, so back to this. Hopefully it didn't clear out the, or save it. If you did, you go back to this. All right, so I'm gonna double click this. I'm gonna go back to this again. So there's, I'll make this red now since you saw that video. There's my bike pump, a first situation, a before situation. And then we're gonna do an after situation over here too. All right, so what I'm gonna do next, I'm gonna highlight this bike pump, this pump here. How'd I do that? I just clicked my mouse, dragged over, dragged down, release. You want that whole diagram. I'm not gonna recreate this whole diagram again. Make it easier, make life a little simpler. So highlight it. I'm gonna go to Control C to copy it, and I'm gonna hit Control V to paste it. I'm not gonna use my mouse this time. Instead of using my mouse, I'm using my little arrows on my keypad, my keyboard, just to bring it over. So why? Let me just get rid of this again, start again. So again, highlight, Control C, paste it, Control V. Why don't I use my mouse this time? Because like if I click like the wrong spot, I'll just bring it over one piece. So I'm gonna bring the whole thing over. Therefore, I'm just gonna use my arrows, my right arrow. All right, so this first situation, I'm not gonna change that one at all. I'm gonna take that pump and I'm gonna drive this pump on down. So before I do that, I'm gonna take these particles, I'm just gonna take them out. If you brought the wrong thing over, just do Control Z. That undoes what you just had. All right, so I have the same amount of particles here and there. You will have the same amount of particles if it's a closed system. What you're gonna do now, you're gonna drive this on down by clicking. I can't get both these rectangles to come down. So I'm clicking the bottom one, and I'm just using the arrow to bring it straight down. So bringing it down, maybe 3/4 away, roughly. And then I'm gonna bring this down as well, the shaft there. So I press on down. I still am gonna have the exact same number of particles in the first diagram as the second one. They didn't escape up here because I'm pressing them down. If you ever used a bike pump before, as you press it on down, it gets harder and harder and harder the further you are down. So I'm gonna take these particles, I'm gonna put them back in here. They are still gonna be represented as gases, but I'm just changing the amount of pressure that was in the system. So hopefully I have enough room. If not, I could just, this should work out. So it's still representing a gas, but if you notice, there's just not as much room. There we go. So in the first situation, there's a lot of space. They're colliding because they're gases. The second situation, it is an increase or a high pressure system. There's not as much space down there. So these guys, they're gonna have a lot more collisions. So this would be like taking 20 of you guys and throwing you guys all in a closet. If you're all hanging out in a closet, there's gonna be a lot of collisions. If you're all out into the classroom, there's not gonna be as many collisions. You're not gonna really interact as much as to maybe you guys hang out in the closet all together. So in the first situation, I'm gonna do one last thing. This is gonna be called a low pressure system. Low pressure. And the second one to the right, I'm going to make another text box. It's going to be a high pressure. So hopefully this visual helps you from analyzing a low pressure system versus a high pressure. I guess I'm getting really lazy pasting that too. Low pressure and high pressure. So hopefully you can see the difference between low and high. So the high pressured system is going to have a lot more collisions because there's just not as much space. More effective collisions would be here. I guess I'll put more collisions. Okay, once you know that, please save it. How did you duplicate everything? Frank, I just highlighted this. I just went left with my mouse, dragged it on over, pulled it down, released. And then there's a blue box at least around your diagram, hopefully. Hit Control C, which copies. and then I hit Control V, which pastes it. Control C, Control V. And then I use my arrows just to bring it over to the right. Any other questions before I move on? So this visual hopefully helps you understand what pressure or manipulating pressure between both of them. Please save it and close it. If you guys, if I went way too fast in class, you're more than welcome to rewatch this. I recorded the video for just the reason that some people might not have stuff done in time. So I'll give you a chance to actually rewatch it and do what you need to do. In case I went too fast and you're just too scared to ask. Don't be scared. I'm not gonna make fun of you guys. It's not me. I know you guys understand it. Lost in the wind. All right, the second one up. Next one for the, so that first one is relative to pressure. That's what the example is for. The second one, at constant volume, as the temperature of the gas increases, the number of effective collisions increases too. And I'll talk about the example after I copy this one down. So at constant volume,
Mine showed up like really, really tiny, and I can't see any like the letters or like the words I wrote.
okay, mine did too. I don't know if you could click on the box, you could just open it up. Oh, for your diagram or your text or your notes, which one?
Like where I put low pressure equals less collisions.
Oh, you can make it big. I don't care how big you make it. Make the biggest page you really want to. Once you print it out, then you might care about it. So if you want the diagram to be huge, that's totally fine. You could adjust it. These are your notes. Make them look the way you want. Take pride in it. Take pride in what you do. All right, so back to the second bullet. At constant volume, as the temperature, no, I gotta put volume here. That's what it was. At constant volume, as the temperature of the gas increases, temperature we're talking about now, the number of effective collisions increases too. At constant volume, as the temperature increases, the numbers of effective collisions increases as well. And the last one there for relationships of pressure or gases, relative to gases. As the temperature of a gas increases, the speed or velocity, the velocity speed, so how quick they're moving, the velocity or speed of the gas particles increases as well. They move faster if you heat something up. The velocity or speed of the gas particles increases. Okay, this next diagram, you don't have to put your notes. I'm going to do something really quick to represent. Help you think about the temperature of gases and what happens there in both situations. So this next diagram, you don't have to put your notes. I'm just going to go crazy for a second and give you another example for temperature. So I'm going to insert drawing. Just going to talk my way through it. Okay, so I'm going to represent a couple basketballs. So I have two. Oh, I have a basketball there. I did. All right, I'm gonna use a couple couple basketballs. Basketball number 1. And basketball number 2. Nope, I'm not gonna do number 2 yet. I'm gonna represent some particles inside of a basketball. So again, you do not have to do this. So I'm gonna represent maybe, I don't know, what to put in there. What do I put? All right, so there's 2 basketballs, 1 basketball. And let's just put the temperature of this maybe 32 degrees Fahrenheit. We know that temperature. That's the freezing point of water. I'll take that basketball, I'm gonna copy that all and paste it to the right. Maybe you play basketball and it's 32 degrees out, or kick the soccer ball. You compare it to a nice hot day in summer, which I don't know if we got there this year, 100 degrees. Has anybody ever dribbled a basketball in the winter time? Or when it's really cold out, your ball when it's really cold out, or no? Anybody? Talk to somebody today? Bored here at school, lonely? No, Greg, thank you. I'm sorry. This one's not fair. How about maybe a soccer ball? Anybody kick a soccer ball? No. Oh, Nadina. Nadina. So Nadina, I'm talking to you now. Nadina actually maybe kicked the soccer ball or drove the basketball in the winter time. Nadina, tell me about the ball in the winter time. Is it hard? Is it soft? Is it flat? Is it?
When the soccer ball hits you, it hurts really bad, and it like can leave a bruise.
You ever squeeze a soccer ball in the winter time?
Yeah, it's like really, it's like it has more pressure inside, and it's like harder to squeeze than if it was warmer outside. Like it had more air inside of it.
Oh, so there's more particles in the winter time than it is summertime?
Yeah.
Did you pump up your ball more in the? I'm saying
No.
this whole situation, I don't want to pump it up. So if you don't pump it up, then you're gonna have the exact same number of particles in both situations. You didn't lose any particles. We're gonna say your seal on the ball, it's sealed off, so you can't lose any more, you can't gain any. So number of particles are exactly the same. Now, Dina, the reason why it hurts your foot in the winter time is because that particles around it. So whatever that's made up of, whatever synthetic material, plastic material it's made up of, maybe it's leather for a soccer ball. I don't know what they're made up of. But anyways, I know it's probably gonna be plastic. The winter time, the particles are on the outside. The reason why it hurts so much is because those outside particles, they get really tough. So if you freeze something, they're gonna get more like harder plastic. On like the 100-degree day, it's gonna actually feel more like a smoother, more softer plastic in that situation. But anyways, if you're dribbling a basketball, going to a basketball reference, thank you, Nadina. If you dribble a basketball in the wintertime, you're going to dribble and it's going to go, and it's not going to come back up really quickly. If you dribble a basketball in the winter or summertime, if you feel it, it's going to be like really hard. If you bounce it, it's going to bounce right up really high. So why is it bounce so high? Because these particles are going to move faster and faster and faster. They're going to move really fast in the summertime because it's hot out. So these guys move really quickly when it's hot out. But in the wintertime, they're not going to move as fast. They're going to slow on down. They're not going to move really quickly. So these particles in the summertime are really quick. In the wintertime, these particles really aren't going to move fast at all. They're going really slow. They are cold. You're not going to want to move much. So they're just going from spot to spot. They're still moving. There's still gases in there. but they're not moving as fast as it would in the summertime. So hopefully that example helps you. Nadine, you're opposite with the idea of the particles. So particles move slower. That's why a soccer ball would feel like it's flat. Try it out again over the winter and summer. Think about that concept. Next time you kick a ball, it's winter time or summertime. Think of the difference. Now you can think of those little particles inside there. I'm gonna save my document just because I like that one. First time I went through that type of idea. But anyways, this idea of particles, this yellow behind it. The idea of particles, another way you could think about it is, I would say, when are you more active? Are you more active when it's 32 degrees or 90 degrees in the summertime? Most of you guys are probably more active when it's the summertime. So you guys would rather go for a walk when it's the summertime. You'd probably rather maybe do more outdoor activities. Wintertime, you just want to snuggle up in a blanket and just hang out maybe by a heater. I don't blame you. So that's another example for that too. So that's true for velocities, true for effective collisions. Questions on that? All right, so you don't have to put that in there. I threw it in there just to add that for maybe next year. All right, next up is combined gas laws. Play a video here. Combined gas laws. Show everybody John's grades. Okay, I'm gonna play a video on combined gas laws. I'm gonna use the next topic.
Hey, it's Professor Dave. Let's talk about ideal gases.
He knows a lot about the science stuff. Professor Dave explains.
Let's recall our definition of a gas as the phase of matter where atoms of a substance are in motion and fill their container. If we make a couple simplifying assumptions about gases, we can make some easy predictions. Those are that 1, particles of a gas are dimensionless points in random motion, and the identity of the gas is irrelevant. Could be anything. And 2, that the particles don't interact apart from elastic collisions, bouncing off one another like balls on a pool table. These things aren't completely true, but they make the math easy and surprisingly accurate. So these kinds of samples are called ideal gases. When examining an ideal gas, we want to be able to discuss 4 variables. 1, pressure. This is the force the gas is exerting on its container, or rather, how much the particles are hitting the sides. 2, temperature. This is the amount of heat energy available to be transferred into kinetic energy of motion. The higher the temperature, the faster the particles move. 3, volume. How big is the container? And 4, moles. How many particles are there in the container? So, how many particles, how big is the container, how fast are the particles moving, and how often do they hit the sides? As it turns out, these variables depend on one another in interesting ways that have been formulated into laws. Let's look at a piston. While keeping the moles and temperature the same, in other words, the same number of particles moving at the same speed, if we compress the volume, the pressure must go up. The particles will be hitting the sides more often because there is less distance to travel to hit a side. That means that pressure and volume are inversely proportional. If one goes down, the other goes up. This is expressed in Boyle's law, P1V1 equals P2V2. If we double one variable, we have to cut the other one in half in order to keep this equation valid. Volume and temperature are also related. If we have gas in a balloon and we heat it up, the particles will move more quickly. In order to keep pressure constant, or hit the sides with the same frequency, the volume will have to expand. This means that volume and temperature are directly proportional. If one doubles, the other must double. This is expressed in Charles' law. When we do calculations with temperature, we must always use an absolute temperature scale called the Kelvin scale. 1 degree Kelvin is the same magnitude as 1 degree Celsius, but 0 Kelvin is absolute zero, the lowest temperature possible, a complete absence of heat energy. This helps us avoid weird mathematical issues that would arise if we were doing a calculation involving a negative or 0 temperature. To get Kelvin from Celsius, just add 273. To go the other way, subtract. The combined gas law is like a combination of Boyle's and Charles. Avogadro's law says that equal volumes of gases at the same temperature and pressure contain the same number of molecules. Specifically, that 1 mole of ideal gas occupies 22.4 liters at standard temperature and pressure, regardless of the identity of the gas. Lastly, all the variables correlate in one equation called the ideal gas law. This also contains the gas constant R, which makes these calculations intelligible in our man-made units. There are a number of values for R depending on the units, but we will predominantly use this one. This equation is useful when we aren't looking at a change, but just to know the values of all 4 variables at once, like in this case. We could know the pressure, temperature, and volume of a gas, and quickly calculate how many moles of particles must be in the sample. So if you were looking at a sample of gas and you have 3 of the 4 variables, you can solve for the 4th using the ideal gas law. If you are given some initial conditions as well as some final conditions, you can use one of the other laws to find the other information. Just plug in what you know and solve for what you don't. Let's check comprehension.
Okay, we're not going to check comprehend right there. We'll do some examples together. Another note, I apologize about that video. That man missed a button on his shirt, so it was a little inappropriate. So apologize if it offended you. All right. Moving on forward. So now we're going to talk about combined gas laws. And combined gas laws are going to be something that's going to be in the reference table. We're going to figure out a formula for that soon. Combined gas laws, if you're checking out the video image, or maybe you just got rid of the video image of this. Combined gas laws are going to be on the reference table for the last page of the reference table. It's like the 5th one from the bottom. So combined gas laws, it says P1 V1 divided by T1 equals P2 V2 divided by T2. P stands for pressure, V stands for volume, T stands for temperature. I'm going to highlight these as we go through all the formulas. And then I have STPC page 1 of the reference table, which will be, we'll see that soon. It's going to be not that, but standard temperature and standard pressure. We'll go through that one as well. So those 2 charts we'll see today. All right, so I'm actually going to write this formula out here. And the best way I think I did it was with a diagram again. Yeah, one last thing before I do get to that, though, I apologize, is ideal gas law. So talking about these gases, I'm going to make this pretty big. I'm going to make it bold because they love asking what an ideal gas is. Ideal gas law, make this cap for us here too. Ideal gases, so what an ideal gas is a condition where there's a high temp and a low pressure. Conditions of a gas where there is a high temp and a low pressure. I will almost guaranteed the regents, if we have a regents, they will ask you about the ideal gases. An ideal gas is a condition of a gas where there's a high temp, low pressure. If you're making index cards at home, this is one you should definitely make one for. Ideal gases, high temp, low pressure. High temp, low pressure. Ideal gas, high temp, low pressure. When I randomly ask you that in class, what's about random things of that expectations or things that you should know, this is one you should definitely know. Actually put that in the wrong spot. It should be below, above that last thing. Ideal gas conditions where there's a high temp and low pressure. High temp, pressure. Okay, now we're on to combined gas laws. So we're going to recreate this formula. It's on the reference table as well. We copy and paste? I'm not sure. Let's see. We'll save us time if we do that. Okay, so you guys don't actually have the screen up, some of you guys, so never mind. All right, so in this text box, we're going to recreate this formula. what I'm going to do, I'm going to just hit Control B to make this bold. I'm going to put P, capital P, and then 1, which is Control, comma, subscript 1, Control, comma again. So that's pressure 1 times V 1. I'm going to go back up. On the same line, I'm putting equals. And then maybe tab it. Nope, don't tab it. Space bar some more. And I'm going to do P Control, comma, 2, Control, comma, times V2. So you're basically going to mimic what that formula is from the left. And this is all divided by, so that's why there's a dashed line there. Go on over to the right, there's going to be a dashed line divided by. So if you have the screen up to the left, you could copy and paste it. I know not everybody has a screen up, so that's why I'm going to just rewrite this out again. Divided by, enter, T1, and then T2 to the right. Make this a little larger so you can see it. I took my equal sign and put it on the same line as my dividing, just to make it look more even. All right, that is the formula for ideal gases. Something like that. So again, it's in the reference table as well. Does anybody need help with recreating this formula? Again, if you open up the doc, you could copy it and paste it right in if you don't want to go through this process. This situation, the reference table could tell you this as well. The pressure's units could be a couple different things. So P stands for pressure. Pressure could be measured in pascals, which if you look on the reference table, first page of the reference table, you can see selected units. And right there on the reference table, you can see pressure. Pressure is measured in pascals. So 1 unit for pressure could be PA, which is pascals. That one you're probably not familiar with. Maybe it's KPA, kilopascals. It could be torr, another one, or it could be ATM. So basically, a unit you probably never seen before is probably be representative for pressure. Volume could be measured in a couple different things. It could be measured with the SI unit of liters, maybe it's milliliters, maybe it's centimeters cubed. Those are all units for volume. There's more, but those are some units for volume. And temperature, the units that we might see for temp could be Kelvin or Celsius. Maybe Fahrenheit, then you have to convert it. So if you have a number with a unit of any of those, pascals, kilopascals, torr, or ATM, that's going to be pressure. If you have a unit that's devoted with liters, centimeters cubed, something like that, that's volume. If you have temperature, hopefully you know it, Celsius, Kelvin, or Fahrenheit. Okay, let's check out an example. So hopefully we get through one example for class today. If not, don't before we get to the example, we have standard temp and pressure. Maybe we'll get to the example. Additionally, when you're dealing with a pressure or a combined gas law, sometimes they have STP. They talk about standard temperature and pressure, STP. So STP stands for conditions here on Earth. It's not conditions on Mars, it's not conditions on the moon. So like pressure or temperature, that would be constant here on Earth. We're not taking it and putting it into like a pressurized system. STP, standard temperature and pressure. You're not expected to know this, but I will say STP all the time. Standard temperature and pressure, red flag, conditions here on Earth, or red flag, the values are going to be on page 1 of the reference table. So standard pressure, another unit for pressure, you can see here, kPa, kilopascals, atmospheres as well. So 101.3 kPa, kilopascals, are conditions here on Earth. 1 atmosphere are conditions here on Earth. Standard temperature, we have 273 Kelvin or 0 degrees Celsius. So again, you see STP, you think of page 1 of the reference table, another red flag there, standard pressure and temp. So those are their tools. So anytime, because the reason why this is here, because a lot of times they're going to ask about STP in a situation. So basically this calculation is going to be 2 different chambers. You have 1 chamber, kind of like my bike pump. You have 1 chamber with 1 condition, and then you're going to have another chamber with the second condition. And a lot of times they're going to ask you to solve for like just 1 variable, so that maybe they ask for that, and they give you everything else in the paragraph. So let's try one example out. Example number 1. I have like 10 minutes to go through it. I'm going to take my drawing board. I'm going to go to highlight this question. Highlight the question, and I'm going to copy. So you should all be doing this as well. Insert drawing new. So again, go to your highlighter, highlight all the information, copy it, Control C, drawing, insert drawing new. I'm going to paste it in here. Control V, paste it on in. Let's stretch this on out. And just like my quote of the day, if you're not familiar with this, it looks scary. You will become familiar with it because we'll do more questions like this tomorrow. The more you see it, the more comfortable you'll be with it, and you won't have questions about it, hopefully. Question reads, here we go. I'm going to highlight the information that's important to me so I can make an inference in my head to figure out which formula and how to come up with a way to solve for this. So I'm going to highlight, same approach as I'm doing here is the same thing I did last time for heat. Question reads, what volume will a gas occupy if the pressure on a 244 centimeters cube gas at 4 atmospheres is increased to 6 atmospheres? Assume the temperature remains constant. So just like that pump earlier in the class, we have a before situation and an after. We have low pressure and a high pressure system. These questions have one situation versus another situation, just like that formula. So we're looking for some stuff here. Let's highlight. What volume? So we are definitely looking for what is a question. You're looking for a volume in the situation. So volume is what we're looking for. Well, a gas, so we're analyzing a gas. If the pressure on a 244 centimeters cubed, that would represent, not pressure, a centimeters cubed would represent a volume. At 4 atmospheres, which is a pressure, is increased to 6 atmospheres. ATM is a pressure as well. Oh, I like that color. 6 atmospheres too. Assume the temperature remains constant. That's huge there. So temp remains the same. I'm going to change my volume to orange because that's a volume and that's a volume. So both volumes are orange. Both pressures are green. Temperature is red. So once you highlight the important information, maybe gas is important too. Okay. So the hardest part is to figure out before and after situation. Next, I would figure out what's given to me in the text above. What volume? So we're looking for a volume. We have another volume here. I'm going to skip the orange from now. So maybe we'll skip the orange. Let's go to 4 atmospheres. I'm going to take this 4 atmospheres. That's going to be a pressure. So the first one I'm going to call P1. So pressure, subscript, which is control comma, 1, equals 4.0 atm. The first pressure is there. At 4 atmospheres, it's increased to 6 atmospheres. All right, so 6 atmospheres, I'm gonna put all the way to the right. So this is all gonna be like the first situation over here. The data for the second situation is gonna go right here. So I'm gonna bring it all the way over by using my space bar. I guess you could tab it too. And the second situation, I'm gonna copy and paste that over to the right. I'm not gonna have enough time to finish this question up. This is gonna be P2, which is 6 atmospheres over to the right. So that's done. Now, I'm going to go back to the orange. We have what volume, and we have 244 centimeters cubed. So after that, I'm going to press enter. What volume will the gas occupy if the pressure on a 244 centimeter cube gas at 4 atmospheres? So those two are really close together. That 244 is going to be the initial, or volume 1. So it's going to be hard to figure that one out. Volume 1 equals 244 centimeters cubed. Yeah, it looks horrible, but we'll fix that. So the first volume is 244 centimeters cubed. That should be an orange. Line mine up. The second volume is unknown. So we're going to solve for that second volume. I'm going to copy that. Bring it on over. Paste it there. So the second volume, V2, is unknown. We're going to solve that one. That's going to be our X. And the last thing for today, the temperature remains the same. So after that, pressing enter, and temperature remains the same. That means it's not going to change. So temperature remains the same. Make your math easy. Use an easy number to multiply or divide. So I'm just going to say 1 Kelvin. If it's 1 Kelvin here, it's got to be 1 Kelvin on the right side as well. So first situation, so I'll call it T1, is equal to 1 Kelvin. The second temperature, T2, is equal to 1 Kelvin as well. Why? Because it remains constant, it remains the same. So it's got to be 1 K here as well. I'm not going to go any further in this calculation. I know it looks a little tricky right now. The first one's going to be tough. The second one's going to be tough. But after you do a few more, you'll definitely understand how to do ideal gas laws. On that note, there's 4 minutes of class left. You're welcome to hang out, and I can help you out with whatever you need. But that's it for today. We'll pick up tomorrow. We'll do more examples on this, and we'll finish up the last topic as well. All right, that's it for today, guys. Have a great day. Make good decisions. Be kind to one another. See you later. See you tomorrow.
Have a nice day.
You too. Thank you. Have a good one out there. Bye, Kim. Bye, John. Have a good one. Thanks. Oh, thanks. I'm glad you had a good class today. Private message there. Good stuff coming up. Bye, Kai. Bye, see ya. Bye, Nadia. Have a good one.
Have a great day, Mr. Brown.
You too, Frank. We'll see you later. See you tomorrow.
Have a good day.
Have a great day, Mr. Brown.
You too. Enjoy that walk in the rain. Enjoy singing in the rain today.